you re-enter into Earth's atmosphere, temperatures can reach upwards of 1500 degrees C and even higher. And so we're focusing on materials at ultra-high temperatures. Some of the work we've recently published is measuring thermal expansion on materials like titanium diboride. When we did these experiments, we were able to levitate the titanium diboride and heat it all the way up to 3000 degrees C. We were actually able to get the thermal expansion around 1000 degrees higher than conventional measurements, right? And so this really could have only been achieved using the conical nozzle levitator system, right? Thanks to its ability to do these experiments in a containerless environment where we could choose the levitation gas to be one that was inert.
Earth was formed because of impact events. We have to understand what the Earth is made of in order to understand how are deep earthquakes happening, what is happening in terms of volcanism around the globe. For this study, we started out with a synthetic chondrite material. Chondrites are the building blocks of Earth, and we heated that in the levitation furnace. So we did some temperature and time series experiments. In the past, scientists have used isotopes as barometers and thermometers and ways to predict the pressures and temperatures at which a process occurred. But in these experiments, because of the unique setup where you are fractionating them in the presence of a flowing gas, we were also able to determine the effect of that gas flow on the final fractionation. And so in this way, we created a model of an isotope velocimeter.
When we collect an atmosphere sample and look at the isotope composition of it, can we get with better precision what some of the atmospheric processes and airflow and wind patterns were happening within, say, this thunderstorm complex? My research has focused on the use of water isotopes in the realm of hydrology, meteorology, and climatology. We suspended these water droplets, and then what we did is we looked at what happened to the concentration of isotope to the droplets. A lot of the often cited model that studies this work assumes that the vapor from the raindrop goes away. We developed a fairly simple model to explain evaporation from the droplet was re-exchanging back with the droplet again.
When I started MDI, the goal was to use containerless processes to study materials in extreme conditions and non-equilibrium conditions.
At MDI, we develop and build custom instrumentation. We have two primary instruments, the conical nozzle levitator, and the second instrument, the single-axis acoustic levitator. HTCNL, or high-temperature conical nozzle levitator, is designed to process samples at extreme temperatures, and it does so by using a gas stream. You can select what type of gas, and that's flowed through a converging diverging nozzle on which the sample initially rests, and then once the gas is flowing through, the sample levitates inside that nozzle. And we pair that levitation with a high power carbon dioxide laser. And so not only can you process samples, you can also characterize them in place, in situ, as they're in their molten state.
So we have a system that combines two lasers that work at different wavelengths, and that's very versatile. It enables extremely high temperatures and also very flexible heating of all sorts of materials, from metals through to the oxides and the new high temperature materials that are under development, carbides and nitrides and things like that. I think a big area is optical materials, because that really takes advantage of both aspects of containerless processing. You need very high purity so that you're not contaminating the optical signal. You also need to make glasses that have improved properties. Containerless processing or levitation is a really useful tool for referencing those kinds of materials. When we build an instrument for a customer, it's a very customized instrument very often. We start with the base instrument, and then we talk about what the customer's looking for in terms of accessories or specific application. So there's a combination of hardware and software that can be involved in customizing an instrument. The thing that makes MDI's HTCNL attractive is it's well integrated. It's designed to be turnkey, so the user can use it for research and not be too concerned about the operations.
A user who wants to process a sample can very quickly access settings for the gas flow, the laser power, heating rates, and also record temperature data. at whatever rate they would like. So if they're interested in the cooling behavior or perhaps recolescence of their samples, all of that can be captured very easily from the software interface.
There's a lot of interesting science and technology that involves working with liquids around ambient temperature. So the challenge there is to have stable drops at around ambient temperature and to be able to control the solvents or the composition of the drop. And for that, we use a different technique called acoustic levitation. So the desal really focused on temperature range from about -20 to +50 degrees centigrade. So aqueous solutions and liquids, sort of biological type materials, that's been used in working with pharmaceutical materials, food materials, and even climate research. Because it's in an enclosed environment, one can adjust the humidity and the temperature, and that's useful to control exchange between the sample and the atmosphere around it.
The single-axis acoustic levitator is very easy to approach. It comes with all of the hardware pre-built. It comes with a software package that provides all of the controls necessary for acoustic operation, temperature and humidity control. Then the user can really focus on their samples and the types of experiments that they want to do. Most of the accessories to the acoustic levitator come in terms of characterization probes, whether that's infrared camera to study temperature of droplets, or even spectroscopic probe that we could align with the sample.
MDI really works at the interface between basic and applied research. We have different kinds of partnerships. We've been working with the Advanced Photon Source and the Spallation Neutron Source to build our instruments into their beamlines so they become part of the user program. We have experiments on the International Space Station, and in fact currently we have a very interesting project with some collaborators at Arizona State University. We're putting on a split nozzle so that we'll be able to actually drop molten samples and let them free fall and then capture them and measure the heat content of the liquid. So that's a very enjoyable part of MDI, I think, is the fact that we do have a variety of projects and we're always open to new ideas.
MDI provides a convenient way to try out an idea using these levitation methods as well. We very often collaborate with people who have an idea of how levitation might be useful to their research, and we'll collect preliminary results either by hosting somebody here or shipping samples back and forth that we can process with our levitator. We have several decades of experience with these instruments, and so we bring expertise from a lot of different disciplines, ranging from physics to mechanical engineering, electrical engineering, and can very quickly produce an instrument tailored to a user's needs.